particularly in a networking problem, you will send some data into your system, and the system may have, let's say, parallel engines of this, no longer the legs, okay? It is a parallel set of engines that work over, let's say, the processing the BT, right? You know, BT is using simultaneously many processes to, download, upload, whatever you want to do, okay? So maybe the producer will be only the guy that's sending you the seed, okay, sending you the data. Now the consumer may be the parallel threads, okay, parallel process in order to understand what are the contents and try to allocate this space and put the data trunk into your disk, okay? One more practical example is, I would say that this is imaginary because I don't give you codes, okay? You can later on, after you learn all the things, you can try to implement it. What is that? Parallel POP with quicksort. So I would say there's a parallel quicksort, right? So you call, let's say, I just use a very simple example. I just call POP twice, okay? You have a parent process. You receive some data, people ask you to do a quicksort, okay? Then you how many of you know quicksort? If you don't know quicksort job, this course I want to do the job. Okay? Yeah. And this is not a short, it's quick, okay? So the quicksort is like that, right? You find kind of people point, I don't know what is the luck, okay? Maybe you're doing randomized quicksort. Hope that you find a midpoint, hope, okay? Then kind of dissect the memory into two pieces. Why not we do a fork over that point before we continue to do the recursion? Right? We are not doing recursion, but we use this chunk of data called fork. Now you are implementing phase 2. You understand that after you do the fork, all the memory will be duplicated, and that's why when we separate the two pieces area, I do a fork here, I will get that duplicates. And here I will also get the duplicates. And you play your, quicksort recursion algorithm over this half of the range. Maybe you are not satisfied. You can continue to do it, chopping off this smaller chunk of data using the recursive properties. But before the recursion, you call fork. Then each recursion you can assign, let's say, each process is only allowed to sort 10 numbers, let's say. Okay? Then you call recursive fork again and again until that trunk get only 10 numbers. Then you do this normal sorting, and then this guy, the parent, co-waits. Okay? Now you are doing pipeline. Now you know what I'm talking about. Wait for 2 times. Okay? And after 2 times, you will find that 2 of the child comes back. Good. I can concatenate back all the data. Maybe the concatenation is to write to a file or print to the screen. It doesn't matter. Parallel sort. Okay? And yeah, you can think of other ways. Let's say, I have a merge sort. Okay? A merge sort is a little bit hard. Okay? If you're doing merge sort over this area, okay, I particularly choose quicksort. And if you want some description to be welcome to do so during the break. Okay? Why merge sort is a little bit hard. Okay? Should be no question, right? Because you don't know what I'm talking about. Okay? Yeah, that's why it's the extra. Okay? Well, this is other model. Other people invent, okay, other ways to do this kind of IPC. We basically have 2 IPC models. One of the models is included in this course, which is using what we call shared object. Okay? There's a shared object, maybe a file, maybe a shared memory, and I put something there. And we have multiple processes. Let's say the P1 and P2. P1 puts something into the box. This is the box. And P2 knows that you put something in the box. That means that you finish certain computation, then you get the result. And put the result in here. P2 consume the result. And this is producer and consumer. And if I change the other way, that will be another type of RPC model. Okay? And we always manipulate this shared object, maybe a file, maybe a variable. Okay, later on I will use some, then if you come early, you see that you're using that word for cross-row puzzle there. Cross-row puzzle, not crossword puzzle. It's cross-row puzzle, and actually when you look at the cross-row puzzle, there's no data, right? There's no trying to write something else on the file but want to control traffic lights, we can also use this model solver. Okay? And our model is what we call message parsing. Okay, the message parsing model is particularly useful under a supercomputer or cluster of computer environment because they work like this. They send messages. When I reach certain, let's say I do a computation, I finish a part of it, and I want to send the data from one process to another process. Okay, so this is message parsing. Well, basically, the networking is one of the examples of I think that's CSCI 12.30. And we do have other course over supercomputer. Okay, so if you're interested in it, you can take a look at a library called MPI. Okay, or OpenMP, message parsing. Okay, it's OpenMP, MPI, so and so forth. Okay, and we won't include this into our course, but our department already has this kind of resources. What is that? Yeah, our department. I need to use VPN first. Yeah, some people tell me that VPN sucks, right? These days. Yeah, some tutors tell me that they got a broken VPN. It's broke every 30 minutes. Yeah, so we have Unix. Our research lab. I can't remember. Yeah, there's some. I'm missing. Does any people know where is that?
Linux they are API.
Yeah, I know, but there is a dedicated supercomputer server. High performance. Yeah, I can't remember where is it. Yeah, maybe during the break I look it up. Okay, it's a high performance cluster using MPI. Okay, and you well, usually you ask some supervisor to sign a form in order to use it. Okay, and don't ask me. I'm not your supervisor, I might cost stuff on that, okay? So if you like to know more, ask him. Ask him. Okay. 有邊個洗翻啊？
我啊，我陣間出嚟講得。
Oh, sorry, so happened that we compromise, okay. Okay. Right, race condition. So what is the race condition here? I draw a graph here again, okay? So in order to understand what is race condition, previous story I have here is something like this. Okay, yeah. Make sure I'm fast. Okay, you know in secondary school I always fail in my last subject. Okay, and this is why. Okay, yeah, we have a block. Block is not set. Okay, our cost from here. Okay, some cost coming in this direction, some cost coming in some directions. Of course, this area we usually call a share region. Okay, that area I circle it. But in real world, we have traffic lights. Okay, traffic lights. And this one, it's or not purple. Okay, or pop. These are traffic lights. Okay, this traffic lights will control the crossroads so that what is that? Only at the same time one car can step on this region at the same time. Okay? And if we don't control it, these two cars, okay, these are two cars here, we just race it, right? They want to race to this area, occupy it. I don't know why they want to occupy it, okay? Or just try to race to that point and take the road ownership and get past to its destination with discount turn, discount corner turn, okay? And they need to get it. And this is what we call the race, okay, not the race condition, okay? In computer, this is different. Race condition is not about two cars racing to get that items. It's about our computation thing is shared whenever it's shared. Okay, so what the thing that is shared may be the pipe without any control of the kernel pipe. Kernel pipe has control to shield all the race condition. So no two cars can race to get the pipe. Okay? Share memory, no control at all. File, no control at all. Only pipe has control. Okay? Now let's say we have a way to have two processes write to the same file together without any control, then what will happen? Let's say they race together, want to occupy the first pipe. Then it is just a reverse of the race, right? Race means that the first guy to reach that slot will win the game. Let's say this time these two guys want to race to this file and get it first fight ownership and right to it. Then it will be the last guy who will reach there, will be able to write it. Okay, so just a reverse of the race. And when this happens, so I highlighted all the words here, you will get some unpredictable results. If that, and you allow that happen, and you don't lock up something to give that process exclusive ownership, and the unpredictable result is very interesting. Okay, I had FYP team. Okay, how many years ago? Maybe 4 or 5 years ago. Okay, they are writing threading program. Threading is a multiple execution within the same process. And they forgot to lock up something. And the thing that they forgot to lock up is access the database. Okay? And access the database, you don't need to lock up nowadays, okay? But in their production environment, they have to lock up something, and they forgot to lock up. And usually when they demo to me, there is no problem. When they demo to the marker or presentation, then the pop up error. Okay, so later on I can tell you what is going on, and let's see some of the illustrations. This is a fake illustration because it seldom happens. The animations here is just a theme. Okay, so I tell you don't print it. Okay, we have two processes, process A and B. Okay, they are sharing the same memory. Let's say you imagine it is a file. Imagine it is a file, may not be a shared memory. Now you want to write to them, okay, to do it. They want to write to it, okay? And their operations is very interesting. One is want to increment it by 10, and one is want to increment it by 10, okay? So when you first time hear about this problem, you will say that, yeah, no problem. Or one guy want to add $10, one guy want to decrement $10, my wallets won't change. Right? My wallets always get back $10. This is what you think. But in a program, especially when this operation is broken down into lower level languages like this, okay? So a high level language is usually you say that, oh, I attach to the shared memory if it is file that's not attached, you're doing fopen, okay? So I use a generic name called attach here. You can imagine this fopen. And after fopen, I try to use, I don't know what's your way, fprintf or fwrite, doesn't matter. Try to write to it, but before you write to it, it will change its data before you write. Okay? And in lower level code, this one add 10 to x may be that complicated. You first load that thing from memory and keep it in a CPU register. Let's say the register is called A. Okay? And then you increase the variable inside the register by 10 when you do an add, and then write that register value back to the memory. And that's the end of this original high-level language line 2. Okay? So it's actually broken down maybe more than 3 lines, but it's very typical that you will break into these 3 steps. Now the animation is like this. This is normal case. For the normal case, we have let me highlight here. The state here. Oh, sorry. The state here. I cannot highlight it well. Okay, the state here. I imagine that in our scenario we have one CPU, one core. Okay, and that scenario will only show the state either is ready or running. So both are ready, that means that the CPU won't choose anyone. The CPU executed and unfazed. Okay? So the normal case is like this. We have a register value, it doesn't matter because we will load something in the register. And when we start executing, the CPU tries to pick one of them. This guy is running, this guy is still ready. And when we go on, very easy, right? We have 1 step, 2 step, 3 step, okay? And when 3 steps finish, we'll get a 20 here. And the process speed do the same thing when we get the CPU attention. 1 step, 2 step, 3 step. Okay, so you may be puzzled and hey, you say that register A on both areas because on the code needs the register A. Now remember, whenever you have a context switching, it means that I will reserve that register value in the kernel and then load the previous program register save of process B. So although I write down both of register A, it means different register value. It's being saved and loaded onto the register. Okay? So this is for normal case, 1, 2, 3, 4, 5, 6 steps. Now I give something abnormal. Abnormal case is like this. I say that context switching may happen at any time and any place. So maybe we can have this execution sequence. The sequence is first, process A being selected, you will load the memory into register A, and then what? Suddenly, someone hit the keyboard. Generate an interrupt, and after the interrupt, the schedule 7 context switch. So happen when I context switch, it is process B, and process B also load something from X to register A. Okay? Now imagine if you don't understand this case, imagine that you're reading file, right? You want to increment the content inside the file. The content originally is 10, you want to update it to 20. Of course, you have to load it from the file, right? And when you load the file, okay, it's actually the same as this step. Now, after this load, no matter what is the execution sequence, it may not very funny. The funny case is, I add 10 here, then I will context switch again. This guy managed to have minus operations. Then what? Then I don't know what. What is that? This is 10, but well, who runs first? Who will update this register X? Register memory X first. So let's say this guy execute first, then X will become 20, and this guy execute later, it will become 0. Or vice versa. This guy execute first, then write 0 there. This guy execute next, you update it to 20. Okay? But never 10. You never get 10. You will either get 0 or 20. Yeah, that's just funny, right? Then you can try this game with your mother or your father. I don't know, ask father for $10, give mom $10, okay? And by magic you get 20. It's not possible, right? It's not possible in real life, but in computer it is possible. But look at the execution sequence. How often you will have this case? After executing this 2.1 in process A, and you have context switch, and so happen that you execute line 2.1 of process B, very weird. Right? You will always execute from 2.1, 2.2, 2.3 because this speed operation just needs 1 millisecond. Right? 1 millisecond and finish it. So that's why this kind of bump, okay, we call it race condition, and 99% of the execution you won't find any problem. Never. 99% of the case. Only a very weird case, 1 or 2%, you will get that bump manifest. So programmers when you tell them there is a race condition, they will think that, oh, how come, okay? Then they will look for all the shared objects and try to lock all of them. But you never tell them that there's a potential race condition happening in your program. Then they don't know. And they never aware of it because this kind of execution is very weird. 99% will be okay, 1% is problematic. I can only give you a counter example which system always has this kind of bug. QSys. Have you seen the QSys ways of bug saying that Microsoft server get deadlock? I see many times. Yeah, I don't know whether it's my in Cantonese 讲韩文 okay, or I know what is the problem. I always say this, okay? QSys always still show me deadlock, okay? And the deadlock is actually one of the symptoms when you get race condition and you manifest, then you will have some problem, okay? QSys is rocks, right? they turn this probability upside down. Okay, yeah, rocks. Okay, so any problem, race condition, yeah.
Why are there two registers A?
Oh, I just told you, not two register A. When you do the context switching, the old process using register A, right? It will back it up to the kernel because you have to load another process up. So another process before that has that previous state. Okay, this is not shared. It's loaded just like the game state. Right? Any problem? Any problem? So this is not quite convincing, okay? But when you think of this operation is work over files, then you will immediately find that, oh yeah, it is the case. It is the case, right? You load from your memory, from your file load or to your memory, you update your memory, then flush it back to the file, exactly the same. Okay? But very, very seldom you will have a problem. Okay? So, the solution to it, very easy. Really very easy. It's mutual exclusion. So what is the meaning of mutual exclusion? We have two processes. Yeah, make it like this, okay? Do you know why you want to use this symbol? You never know. Yeah, you want the symbol is like this. These three guys are actually really three guys, okay? They are holding hands, like a circle. You don't know, the original three circles are hand, okay? And then the arms, okay? And they form a circle. Okay? And in my point of view, it actually, are they holding hands? Who cares? No, we don't know. Actually, maybe they're raising something. So, what is the solution is the mutual exclusion. This is just a noun. This is a noun. The noun means I want to achieve this thing. Whenever I touch that memory, I will lock up every process. Now, not meaning lock up the memory. It's a kind of interesting. How can I lock up the memory? Yeah, this is an address, right? I lock the address. It's not the case. It means that when I access it, I will try to lock up other guys who want to access that piece of memory. Okay, so what is the meaning of lockup? Maybe this guy is doing the load operations, and load operations may be a system call or maybe other things. When this guy tries to load, this guy will get suspended. Okay, or even terminated. Yeah, touching the terminated. Okay, yeah. So that you will have only one process that can access to that piece of memory, then every problem solved. Right? What is the meaning? The meaning is I start loading this two program. When this guy touch the process A, touch the memory X, I lock up B when B try to execute 2.1. Okay? When load 2.1, then no, I'm using that thing. Okay? You should not touch it. Okay? And this is the illustration what we want to achieve. Okay? And when we know what we want to achieve, then back to programming, we have to think of one systematic way to set up this kind of protection. First of all, the protection is you need to know what is your target. Yeah, this is target shared memory. Okay? And you know that that particular memory is going to be shared. Let's say we know that we will share a file across different processes. Then the file will be our target. And another target is we call critical section. It is not the memory. It's the codes. The codes. The codes that you try to read or try to write that shared object. Okay? So we have two guys. One is a shared object or the targets I want to protect. And there are operations that will touch my target. When the operation tries to touch my target, before doing so, I will lock up something. I turn on the lock, okay, or I turn on just like what? Just like the outside. There's something in the drama, in TVB drama, okay. You see the light outside the operation room of a hospital. When the light is up, that means that someone is in there. When the light is off, someone is go away. Okay? I mean, go away means go away from it. Okay? Not pass away. Okay? Go away. Okay? So this is a lock and unlock. You try to lock that region, and I know that I will touch this shared object. Okay, I set up the region as tight as possible. I don't want to lock. Okay, I have a long program running for 2 hours. Maybe I lock up the entire 2 hours. Okay, no. Okay, you should only lock up the code related to the shared object. Okay, so I think you are not very aware of how to construct this code. I will give you some real life example. The real life example is this. You will understand immediately. What is that? This is the toilet. Okay? There's not any special rooms. This is the most important room of all, a toilet. So the toilet should be shared, right? You won't own a toilet seat in this building, right? It is shared. Okay, so this is the shared object. Okay? And you are the processors. Okay? And you go there to do critical things. So this is critical region. The code is okay, you go in, you execute some code, I don't know what's the code. Okay? I don't tell you. Right? You maybe put a lunchbox there. Your code. Very important. And you always access that shared object. You won't go in there and don't touch the shared object, right? Yeah, think about it. What was the time you go in there but don't touch the shared object? When I say this or okay? And now imagine that how you lock up the entire room. Very simple. Before you execute any critical codes, lock up the door. Okay, lock the door. Then you execute a critical code. Okay? And after you use all the things, okay, you unlock it and go of the room. And how about other processes? Other processes, before they can execute their critical codes, okay, they will check the lock. And whenever the lock that is occupied, then they will be suspended outside the toilet seat. Okay? And of course, there are some naughty processes forgot the lock. Okay, they will try to rush in. Okay, but you know the lock should be safe enough to pop that off. Okay, so this is an illustration, very important thing. Okay, and now you understand what is the lock purpose. It's to notify other processes, please stand by, or not stand by, I would say that please be blocked, or please be suspended outside the critical section of their critical section. And after I finish using a shared object, I will release the resource by unlock it. Okay? So there are some naughty processes, maybe they remember to lock it, but forgot to lock. Yeah, but I don't think that this is applicable in this example, but you know that. How can we go in and don't go out? Right? Yeah, there must be some ninja there, right? Go in and go out. Yeah, some ninja. Okay, although I don't expect it will happen. Okay, so this is a very it's illustrative enough, right? You never forget this case anymore. All right, so then we know what are the shared objects. The objects that allow people to touch it, to write it, to read it, okay? And then the shared objects, if we don't protect it, I don't think it's in real life something also happened. Yeah. In this case, okay, if you forgot to lock it, okay, and this shared object, some people outside there will rush in. I'm not experienced. Okay, so many times, okay. Yeah, some people will try to unlock it and pop. The one inside there gets so shocked and shut down. Shut the door. Shut down. Okay. And this is a race condition. We have a disaster if I don't protect it. Then we try to set up mutual exclusion properties that holds over the shared object. Okay. Then what? Then you are going to define for every different programs. Okay. The program, that's not process, right? Because I'm talking about codes. For different programs, you have to set up a critical section. And whenever you got a critical section, you will lock the program up. Okay? So I can let you to see some of my codes. Okay? Some of my codes is talking about the locking mechanism, but we don't have the time to talk about it, so I will give the code for you for free. What's that? Is it the locking? No. Yeah, I have to find it out. What is the? The list.h. The lock. Nope. The lock. Yep. I cannot find it yet. Yeah, maybe later I find the lock and then show you. Now basically this IPC is actually setting up some of the share memory. This is share memory.h. And I set up some protection. This is the lock that I will later show you, called SDM74. Okay, and I implement most of the ways thing using the signal, so and so forth. Later on, we will show you more. Okay, and then we define the critical section, and the critical section you have to implement the lock as well. Okay, so how to implement the lock? Well, you maybe don't know. Maybe some of you have heard of it. Oh, it is some locking. Okay, who write Java and heard of the ways and notify. No one write Java from here? Thank you. Oh, someone should know how to write Android apps. Oh, I Android sucks. Okay, so we can't really write wait and notify. Okay, so if you already know wait and notify, then you know the wait and notify is actually the implementation of the section entry and section exit. Okay, so if you understand this is the way, then we can kind of understand why. Back to my questions in week 1. I asked you a question. Hey, I give you a CPU 2-core. Only I'm 2 CPU, okay, in a monocore, okay. It's never two times the performance of a computer system of one CPU. It is actually one thing is you are not always writing a program in parallel. And second of all, although you write a program in parallel, you may have a virtual exclusion problem. You have to exclude some of the codes that go parallel with you. If some codes go parallel with you, you will have race condition. Okay? So you have to block it up. Let's say this. You won't allow all guys here doing something in parallel. No. You don't do it, right? Yeah. Of course, the entire system performance is the best if these three guys do it in parallel. Okay? But you don't know it, right? Know it whether it's possible or not. So in here, if we have three shared objects, then we solve the problem, right? If we have more shared objects and these 3 shared objects, each of them you need to be mutually exclusive access, but you have 3, and there's no problem. But in computer system, it may not happen, right? Because you always access the same hard disk. You access the same piece of memory, same printer, okay? Then here will be the bottlenecks, or maybe it's not a bottleneck because you want to uphold the correctness of the program. You cannot have the full speed, and this is another reason that you cannot have a parallel computation going full speed, because you have to protect something, okay? So this is about the thing and how to implement it. I will start for a while and give you a break. I know that this part is very boring. Okay, so how to implement it? First of all, implement that lock. Okay, it's not easy. Okay, and it's already go through many years of research, and we reached a certain maturity now. We have some state-of-the-art implementation, but before it, you have to know why or how we implement it. So we have some requirements. The first requirement is the 2 processors, no two, okay? No processors could be simultaneous inside the critical section. Yes, we know it. Second, what does that mean? No assumption should be made about the speed and the number of CPUs. So what is the meaning? The meaning is, you can go back to the toilet example. Okay? What is the meaning that you cannot assume the speed of the CPU? Let me change a bit. You cannot expect the speed of the code execution of certain process. You cannot expect that, say, Patrick goes into the toilet, okay, forget about the lock, okay, I time it, 30 seconds, come out. Okay, if 30 seconds don't come out, I go in. Okay? Yeah, then this is the assumption, right? You can assume 30 seconds is enough for him. Okay, maybe he needs 30 minutes. Right? So this is the assumption that I talk about. Never assume the speed. to be able to block other processes. Okay? What is the meaning? The meaning is there is no one in the toilet, but it is locked. Yeah. Don't allow your code to execute in this way. Okay? Your code or system of codes can lock up the entire toilet, but no one is executing critical things. Okay? And that is a big problem, right? The last one is hard to understand. So what is the last one here? No process have to wait forever in order to enter its critical section. So what does it mean? The meaning is it's not about someone staying in the toilet forever and don't go out. Yeah, this is a disaster, right? It means that you have a system of processes. Everyone can go in the process, but I don't know why. In your implementation, there is a poor guy, really poor. That poor guy never get the chance to go in. Others can go in. I don't know why. Maybe this is me, okay? I find that, oh, there is someone in the toilet, someone go away. And so happen that when I come back, there is still locked because I don't want to step in. And I'm busy running back from my office to the toilet every hours, going back and forth. But I cannot go in the toilet. Okay? Yeah, and someone smiled and said, you think, oh, I experienced that, okay? Yeah, oh, yeah, very horrible things, okay? And maybe there are someone implement a system like this, right? You find that this is locked, go away to other tasks or go to sleep for 1 second, come back, oh, still locked, go away, still locked, okay? And this is not allowed, okay? So the optimal implementation, after I finish it, I wish to have this execution flow. So look at it from a CPU time point of view. So the CPU time is 2 processes. And when I have dot, it means that it's being blocked. Okay? Now from this point onward, I introduce 2 more color codes in this slide. The color codes here is deep red. Okay? Is section entry. Light green is section exit. Usually I will use paint to be the critical section. If I run out of color, I will use others. Okay? And put together, you will expect that your execution is like this, the optimal execution. I go to the toilet, I find the toilet is not occupied, so I take some time to go in, close the door, lock it. Okay? So you still didn't execute the code inside the critical section. Then I'm staying in the critical section, working. I don't know why you bring a laptop going and working, okay? I see someone do this. Okay? I bring a laptop in, okay? And after I go out, I feel so satisfied, finish the program, okay? Then go out, unlock, okay? But during that time, while you're coding in a room, okay? Someone comes and this deep red code is actually doing similar thing, inspect the lock. I try to lock, but I cannot lock because there's already someone go in there and lock it. So my decision is wait outside. Okay? And this is quite non-human, right? You can imagine your scenario in the first floor or the 9th floor. Then whenever I find, oh, that toilet is full. Okay? I don't know why the toilet is full. Okay? Then you go to another toilet. But here, assume that we only have that toilet that is the only shared object. So I will block outside. And here, when I finish unlocking, I will kind of wake him up, sending a sick cone or some other signal to notify this guy, hey, wake up. Okay, immediately he will execute the critical section code. So this is my optimized result. Okay, maybe the result is not that optimized. Maybe this guy will need to re-execute the entry code and suddenly find that, oh, I don't know why, and other people still in there, I'm too slow, okay? Then you will have another small deep red and then another gray part, but the optimized, the most hopefully happening code is something like this. Any questions? Yeah, the case for multiple processes is the same, as long as we have one shared object. Okay? So this is my goal, and give you some implementation that is really happening in this real world. First of all, now this is the test of your knowledge. The number one implementation is really implemented in the kernel. We call it disable interrupt. So what is the meaning of disable interrupt? The code is very easy. Okay? The critical section entry is disable interrupt. All interrupt is disabled. Then execute your critical section, finish, we enable interrupt. Why? It's work. Or I should ask, what is the meaning of a disable interrupt? Why disable interrupt is so important? Yeah, if you can't remember it, flip it back to the notes about part 4. I have a so-called very important page, and that very important page tells you why disabling interrupt works. Why disable interrupt works? Yeah, the keyword is already in the page. Yeah, read it. Anyone find a keyword? Anyone? Anyone find a keyword? Why disabling interrupt means problem solved? No one? Yeah. So what is the chance that you can have context switching? What are the chances? Clock interrupt, hardware interrupt, exit system call. 3 chances, right? You have a clock interrupt, so the clock interrupt comes in, that means that a particular process used up is quantum, you have to switch to another process. Hardware interrupt, then you have to serve the hardware, and after finish hardware interrupt, you will schedule another process. Exit system call, because you die, okay? Now, think in this way. If it's exit system call, then you don't need to enter the critical section, right? You don't need any critical things anymore, you die. So, we exclude this. Hardware interrupt, okay? Whenever I got a hardware interrupt, let's say hidden keyboard, okay? I will generate an interrupt, and the interrupt will tell the CPU that, hey, I got something interrupt coming in, please handle it. Now I disable it. What is the meaning? Meaning that the kernel or the code that will shield all the disruption from hardware now. You cannot disrupt me while I'm executing the critical section code. One more thing is you also disable clock interrupt. No critical section no context switching is allowed. There's no clock interrupt anymore. Okay? That means executing this part of the code, you are shielded to the outside world. No more signals can come in. Okay? So that's why I said that the part 4 is very important. It can explain many things. Okay? And this is a totally correct solution. We call it kernel fake lock. That is a kernel fake lock. Some people call it fake kernel lock. Okay, that's just bad. Okay? The fake kernel lock down the entire kernel. Okay? But the disaster is if you have copy code and forgot to enable the interrupt, yeah, you have to reboot the chip. Yeah, that's I mean, you disable all the interrupt. No matter how hard you hit the keyboard, how many controls you hit, no interrupt, right? So the keyboard is being a shield up, okay? No one can use the keyboard to notify the system that, hey, I got a problem, okay? So the only way is through hardware cut this power, okay? If you implement it in the wrong way, forgot to enable it. So this is a very attractive and working solution, still working nowadays. Every kernel has this fake kernel lock, but very powerful, very powerful. You should not open up this to user. Think about it, how you write your program. Okay, your way is, whenever something works, then it works. Okay, and I would say that whenever something will break, it breaks. Yeah, Murphy's law, right? Then whenever you forget about it, breaks. That's why we never export this code to the user. The user that is you, the programmer. Programmer never find this. Programmer can only use other ways. Now I introduce to you an other way. Okay, a big fail here. And I will discuss with you I give you some time to think about it. Let me discuss with you what is the solution. The solution is very simple. Why not we, like what we are doing, okay? We go to a store to buy a lock, okay? I buy a lock, and the lock, okay, is just put outside the toilet, okay? And which is shared. This lock is a shared variable. I buy a lock, attach it to my door, okay? And while you are trying to go in, you have to pass through this code. This is the execution of the critical section entry. And an entry code, very simple. When you find that the lock is unlocked, the lock is unlocked, okay? Not turned on, okay? It is 0. It is 0, it is unlocked. So this while loop, you won't go into line 2 for BC waiting because it's 0. So you will pass the while 1, while seems while 1, okay? BC waiting loop here. You will get past that. Then you turn on the lock. You are inside the critical section. Now for another process can look at this code and find that the lock that you buy, okay, is actually turned on. Then I will do BC waiting. So I don't know what is BC waiting. BC waiting could be returning or reading your newspaper, I don't know. But you are not doing your critical section code. And whenever another process executes the code, the share lock will be able to unlock because eventually you will left your critical section. Does it work? I put a big fail here. Tell me why. I give it a break. Okay? And this code has a big problem. What is the problem? Any problem? Who wants to answer? Who want to answer? Yeah? Yes?
佢應該係咪佢 lock 即係佢一個 process 一個 critical section 之後，等緊嗰啲會一齊升。
Can you give me more details? Very close, very close.
But if there is more than one process waiting, and when the lock is set to 0,
yes.
unlock, then the while loop of all the waiting process will finish at the same time.
Are you sure? If I only have one CPU1 core? Yes. Well, in your case, this failed because we have multiple cores. Because he says that it's quite close. He says that what happens if I unlock the door and we have multiple cores, then multiple processes will sense that the lock becomes 0 and go into critical section together. So it's quite close. But how about one CPU, one core? Yeah, give you a hint. This while is just not just one statement. Yeah, while is actually involve multiple statements in lower level language assemblies or so forth. Maybe you get the idea. So idea is very simple, right? You have the test. You have to test the shared object. And then after you test it, you update it, and you may have multiple process, just like this answer, multiple process execute the testing or execute the reading part. And as is already described, so that's why you are very close. You just cannot say that, well, how about every process can execute the read part and then context switch. Right? And then context switch and get the read part, get the read part, context switch. Then you will give an illusion to all the processes, yeah, we open up the door. And every process read that code loaded in the memory saying that lock is equal to 0. So this is a big problem. The big problem is, it seems that you are using a problem to solve a problem. Do you understand what I mean? You have a problem of having a critical section, mutual exclusion safeguard, right? I want to uphold mutual exclusion, but you use another shared object to protect it. This is just a philosophical problem that you cannot solve. Use a problem to solve a problem. Okay? Yeah, I know many people use this way, okay? You have a bug, then you use another bug to cover the bug. Right? You don't understand? All right. So that means that you write too few programs. Okay. When you have a program, I've got a bug. Okay. I shift the bug to another piece of code. Okay. Then yeah. All right. So then this is the textbook example. Okay. So if I'm writing textbook, I will skip this code. Okay. Because this code is totally unusable. This code. This code. This code, someone think that, okay, that log variable sucks, okay? So it not means that, okay, let's change its name to turn, okay? No. This turn is not sucks anymore, okay? Let's take a look why it works, huh? If I remember what I think is, I know that if I use the share variable to protect a mutual exclusive region, I have a problem because whenever we read that variable, we can have space or time that all the process read the same variable values and act accordingly. Then that's the problem. Now, how about we change the game? I allow you to do it. Why not? Yeah, let's read the same value. Your problem is I appoint that value differently into my code. Okay? My code, process number 0, at a point that's turn variable now, maybe it's still treated as not variable. You still share, initialization value is 0. When it is 0, I will go in. Right? I will go in the critical section. When I try to unlock it, I will unlock it to the value 1 so that my partner, process number 1, can start its execution. Okay? This is my partner 1, and partner 1 knows that, because we wait for our value, so with perhaps of part 0 finish its critical section, I will get my chance to go in. Okay? And after this guy will unlock what? By turning the variable into 0. Alright? Do you think that is good? And can you imagine what will be in the long run? Okay? What is the execution pattern? You can already observe some pattern here. Can process 0 execute its critical section twice in a row? Can it? Yeah. Try to understand this code. I give you 1 or 2 minutes to discuss it later. Can it? Awesome. And where it is possible, the answer can easily be found in the title of this PowerPoint. Look at the title of this PowerPoint. Yeah. So what is the pattern? Process 0 execute first. Then can I have process 0 again? Executing the critical section? Can I? No. Right? Because the turn variable for critical section of a process 0 after it's finished, it will turn it into 1. And 1 is not its favorable number, okay? Its lucky number is 0. Okay? And it waits for the turn variable become its lucky number again. And why? Because eventually process 1 will execute and turn the number into from 1 to 0. So the turn variable you will see this switching from 0 to 1, 0 to 1, 0 to 1. And execution pattern is this process 0, process 1, process 0, process 1. Okay? So you can imagine that if this system is not serving 2 dice, it's serving 3 dice. How would you implement it? Maybe it is process 1, okay? Turn the variable from 1, not to 0 now, to 2. Then allow process 2 to 1, and process 2 finish, and just in 1 moment, go back to 0, and then 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay? So this is definitely working, but not good. Not good in the sense that, this is the illustration. It is a very inefficient and also violate the rule that no one outside the critical section stop other people from running it. Okay? Yeah, let's say that I'm the first one, okay? I don't know why I'm wandering outside the critical section. I don't want to go to my critical section, I execute everything. You can stop from 0 from entering it. Okay? So this is not working, and then, good, we have the time. I will give you another textbook example. This textbook example is very famous, okay? And we have a set of algorithms that invented by several guys. Okay, this guy is called Peterson. He invented one solution. Another guy invented another type of solution. It's called Dijkstra. Okay, Dijkstra. You know Dijkstra? The Dijkstra algorithm. What is Dijkstra algorithm? You guys keep all the data structure lessons? Dijkstra. Always on top, right? So that guy actually is not inventing the graph algorithm, okay? That guy also invented critical section implementation, okay? So this is the time before Dijkstra. He think of a solution which is working and it's quite efficient, but very hard to extend. Now I just show you the code. It's highlighted as we wanted to remove the alternation before two page before. And this process is very interesting. You can change the code a little bit. But in this version I give you is those processes pretend to be gentlemen. What was the meaning? Okay, very interesting. You stand in front of the toilet and ask, who want to go in the toilet? Oh, you want to, okay, you go in. Okay? Unless, okay, no one's answering, okay, then I go in. Okay? Toilet is a little bit hard. I cannot stay so long, right? This is the code. Quite long, huh? And it's hard to extend. Okay, so let's go through it together by using our execution flow. Okay, because writing it is reading the whole part. Okay, so I first highlight some of the point here. I don't write down any critical section here because critical section is anything useful. What we're looking for is the implementation of the enter region, how to enter the region, or lock someone within this call. Okay, so that's why you will see the model here. Lock someone in there. As well as how to leave the section. Okay, so to leave the section, that means that try to unlock people while they are inside this model. So you see the relationship, right? The relationship is there is a variable called interested, which is an array. And an array, I just create a shared memory. For the shared memory, I usually give a color orange. So the shared memory, the term, still there. This is the improvement over a string ordination, so we still have the term variable. And then this is the previous illustration, pretend to be gentleman, okay? To ask whether you are interested to go in or not, okay? And in the first, the initialization part, you will find both are not interested yet, okay? And then we will have the unlocking by declaring that, okay, I'm not interested. So in the log part, you will also find the reverse I'm interested in. So let's take a look at the execution flow. Okay, so execution flow here. So here is the description. We can do it together. So the execution flow is like this. How to read it? I have two processes. You read it from top to the bottom. Okay. Here is that the execution flow for process 0. Here is the execution flow for 1, and whenever one description comes, I usually say that it means it turned from 0.0 to 0.1 or vice versa, 0.1 to 0. Okay? Then I have this enter section execute first for 0.0 or 0 start, and this guy goes through from a 4 to 8. So what are the code set being executed? First, I need to compute who is my opponents. Okay, the opponents is very easy. That's why I said it's hard to extend. Is in the design of this program, I only focus on two processes. If I am 0, then the other guy is 1. If I am 1, the other guy is 0. Okay? Then I going through this 4 lines means that I declare my interest. And try to force that this is my turn. This is my turn. Saying that my turn now, okay? And I'm interested. Of course, I want to go in. Okay. So let's take a look at whether you will be locked in there or not. So when you are going to be locked in there, first of all, it is your turn. So you have to say, okay, I can ask the question whether there is other process wish to go in. And pretend to be genuine. Oh, although this is my turn, but you are interested in the toilets, yeah, I give you the toilets. Okay? So why is I give you the toilet? Because when it's my turn and I find that other people interested, then evaluate this employer compound condition becomes true, then I will be in the loop there. Alright? So get this idea, pretend to be gentlemen. So by treating a bit is saying that this is your turn and you are interested, and then you can give another idea. But let's stay with this construction, okay? My turn and you were interested. You go in, I don't go in. Okay? Then we go up to this line. We didn't go outside the critical section entry, and suddenly process 1 comes in. Process 1 comes in and execute a similar code up to line 8. Now we have a problem. The problem is the turn changes. The turn changes from one to another. And well, basically it's easy, right? It means that now the turn is equal to 1 after this line. So I write it here because I run out of space, okay? It means that the shared object here now changes to 1. And now both processes knows that both of them are interested now. Okay? And everyone trying to say that, oh, this is my turn, this is my turn. Yeah, you go ahead and say that it's your turn. It also depends on this interested. Alright? Then after here, you will find that I draw a slide, I declare that this guy go into critical section. Why? Because process 1 have executed and say that this is his turn. And this is his turn to pretend to be the gentleman. Okay? He finally his turn. Later on he will find it is his turn, and person 0 has an interest. So eventually he will stay in while loop. And for person 0, I know that now you say that it's your turn, okay? Then I don't need to respect you anymore. I rush you to the corner, okay? And doing critical things. And after I leave, I declare that my interest is no more. I'm not interested anymore. So this guy will be unfreeze from the waiting loop, and because I declare this here and go into the screen section. Okay? Any questions? Yeah, if you don't no questions, then I give you questions. If I change a bit, what is the deadbeat that I change? Previous case I illustrated in this way. I hard code here, right? Execute from 4 to 8, execute from 4 to 8. Now my hard code changed to execute 4.7, 4 to 7, 4 to 7. And what is the difference? The difference is interesting. Before I say that this is my turn, I declare that I'm interested. So I change the code here, the execution here, so that both processes say that I'm interested now. Okay? And this guy stopped executing. This guy stopped executing. So can you complete the story so that both guys can go into the critical section and leave safely without any problem. Okay? So this is a leave as your homework, okay? You guys when you do a revision, and I just say this is really a homework, okay? Because before the final exam you will ask me, okay? Yeah, usually it's like that. All right. Any questions? Anything you want to know more? So this is a working example. It's a working example. And this BC loop actually has an implementation in the kernel. In the kernel, we call it spinlock. Wow, spinlock.com.uk. Oh, okay, it's called spinlock. Okay, it is a It's a busy waiting loop. Okay, why it's called spin lock? It is a lock but spinning. Yeah, you got spinning over that two lines of code, jumping up and down. Okay, so it's called spin lock. If you want to know more, you can read some of the articles outside. It's really implemented using this kind of I guess the spin lock is not doing while loop, but doing something else, but still busy waiting. All right. So what are the problems about this Peter solution? Why you never heard of Peterson, okay? But you always heard of Dijkstra, okay? Because it's not sucks, right? It's kind of working, but people don't understand some problem before you use it. First of all, some people already say that, wow, this is a wasting CPU time, right? It's just spinning there, okay? And there is some years before I teach kernel hacking, okay? Some people even get in some funny results. What is a funny result? It's not code, it's not right in the slides, things like this. They have two, I don't know why, they have two code, okay? And the two code is using spin lock, okay? And while they're doing spin lock, I don't know why, they have two priorities here. The low priority processes, okay, execute the code, execute the critical section, and can get through a spin lock pause. Okay. Now, what is the problem? I get a high priority process comes in, okay, and their system is very funny. Their system only allows high priority process to go on their CPU, and we only get one CPU, one core. And the problem is very funny. This guy, because it's a high priority process, if you still remember priority scheduling, high priority process always get a chance to go in. We schedule this, and this is the busy waiting loop. It will use 100% of CPU power to speed. Okay? To speed. But this is a high priority problem. Okay? High priority problem, then schedule a neutral guy. And this guy uses full string to speed. This guy never gets scheduled. And what should you do? You set up. Right? First, queue a high system. Okay? And it is really happening as some years before. It is called priority inversion problem. It seems to be reversing the priority, okay? But well, it's not useful anymore. So then, Dijkstra, okay? Dijkstra, think of a very, very good system, okay? The system is, well, we know that busy waiting a lot of work, okay? So he changed the entire system into a new way of thinking. It's not putting that process in the busy waiting loop, but ask him to sleep, okay? And the data structure, actually the data structure, using an integer is just like just a term variable, but we change the entire thing just like setting up an ADT, extra data type, and the extra data type is called semaphore. Okay, and semaphore is like this. I heard that many people, many people carrying me that like a Google interview, Apple interview, Microsoft interview, they all ask this question: do you know what is virtual exclusion? Do you know what is a semaphore? Yeah, because they manage many computers and they will have this kind of a problem that sharing, object sharing resources, and the semaphore is our final solution. That means that is a nowadays state-of-the-art implementation. Okay, every system gets semaphore, and the semaphore, if you go to Wikipedia, you will find something like this. There's a flagging signal in a train station, airport. Okay, it's called semaphore, and the semaphore implementation is just treating the integer as a signaling device. Okay, just an integer. So you will change from 1 to 0 to 2 to 3, and it's non-negative. Never go beyond, drop beyond 0. The minimum number is 0, and they include several calls. Okay, this is the ADD. The ADD includes 2 calls. Okay, and these 2 calls require you to immediately buy some coffee to stay awake. Okay, I will first say this story once today. I will complete it on Monday because it's too important. Okay? Now what is that? This code, okay, is the session entry and the session exit. The up and down call. Okay? So where can you find the up and down call? Semaphore? Up, down, yeah. Yeah. So it's all around every system. Okay? And it's really implemented. And of course, this implementation is I simplified it so that you won't see too much details. I hide all the details and change some of the code. First of all, this disable interrupt is not the same as previous disable interrupt. Okay? You just imagine that, oh, this means that really I don't want any people to disrupt me. And this is the ADP export by the kernel. So it is the kernel invoke interrupt disabling or enabling call. Okay, so these two guys. And I invent one more call which does not exist. It is called a special sleep, a special wake up. Later I will tell you how special it is. Now, this call is, you can treat it as a system call. Using this pass by reference to change the semaphore value. Remember, a semaphore is an integer. So this integer, when you come in, you will try to up it. So what is the meaning of up and down? Up and down means increase it or decrease it. Okay? And it totally depends on its value to work. So when you try to protect that value, remember we have a disable interrupt and an enable interrupt where we try to read it. So when I disable interrupt, I can read it safely. After I finish doing everything, I will re-enable it. Same for the up call. Up before I change and detect this value and also increment it, I will disable it and enable it. Okay? So the up call, the working is like this. I will show you the working now. The working is whenever you try to decrement the semaphore value, usually semaphore value default, really default. The initialization value is 1. Okay? It's 1. So you will be able to decrement it because it's 1, so you will go through one round and decrement it. But let's say it's so unlikely that you find the initialization value or a value that's being used before is now 0. It's now 0. So what will happen? There is a while loop. If you get the 0, you will enable the interrupt. Why? Because you are about to leave this system call and allow people to be scheduled. So after you enable it, you will go into the special sleep. And this special sleep is very interesting. It's per semaphore. So I write structure here and the color here is the kernel color. So inside the kernel, I have a semaphore structure. Okay, the semaphore structure, remember the PID, let's say this process PID 1, 2, 3, 4, you call down, okay, now you really go down. Okay, you will be put inside this waiting list, and I know that you will go into the sleep. Who will notify you so that you will get up again? The partner call. Let's say in this example, the waiting list of this special semaphore for X already put 2 guys into the state of block. They are waiting there. At least 1 or 2, doesn't matter. At least you will go into the checking before you really increment the increment. Now, what happens if I find, before I implement it, I find it 0, that means that there is a possibility that some people, before I call it up, turn it into down, turn it into 0, or there's more processes here, go down, go to sleep, because it's the 0. So when I go to turn it into 1, I will try to use a special wake up, so I say that it's special, because it will look up this waiting list and notify every process here to tell them that, hey, this is the chance, please wake up. Okay, then both processes wake up together, and after they wake up, this guy, okay? After I call the wake up, I will re-enable the interrupt so that the scheduler may have a chance to shoot these 2 guys. Then I finish the system call. What is the story? The story now is someone go down, And before you go down, you say the list that, hey, when you finish something, okay, please bring me down, okay? And now I remember you, okay, because I know that there is a waiting list here. When I finish doing that thing, I wake you up. Is it similar to the toilet example? The toilet example is just the same, right? This is door lock, the door lock of a door X of a toilet X, okay? And the toilet X has a lock there. 1, it means that the lock is open. When it's 0, that means that the lock is locked. You turn on the lock, okay? No one can go in. Now, when you find that the lock is locked there, okay? Then you will wait outside the toilet, and there is a queue, right? There should be a queue, right? Should be a queue outside the toilet seat. Outside the toilet door. Okay, outside the toilet door. Then all people get a number, so you write down the number. Oh, I'm waiting. Then when someone inside the toilet, let's say it's 1357, want to go out of the toilet, it will call the up system call, so that it will unlock the door. When you unlock the door, at the same time, you will go through this list to find that, hey, what are the people that are already sleeping on the floor outside the toilet, okay? Oh, I find you guys. I shake him up, okay? Shake them up, hey, I finished you, and then you guys go in, okay? Then I will wake them up, turn on the lock, that means I change the lock from 0 back to 1. Then I will go on with my job, and you guys go on with your job. What are their jobs? Take a look here. Their jobs is, we need some discussion here. Okay? The job is, after they come back from a special sleep, you wake up, don't sleep on the floor, wake up. Then when you wake up, you will disable the interrupt. Now, this work in discussion because the disable interrupt needs some explanation, right? I don't allow 2 processes to disable the interrupt at the same time. And this sucks, right? How come I disable the interrupt at the same time by 2 different processes? So we have to assume that the disable interrupt only allowed by 1 process only. And that process after is find that okay, it is disabled. And I also find that the S value, this is the lock value, is unlocked now. Unlock means 1. And what? Then I will implement it. And we enable interrupt. It means that I lock the door now. And then I will go in the toilets. So let's say this is 1, 2, 3, 4 can wake up before 2, 4, 6, 8. So what happened with 2, 4, 6, 8? 2, 4, 6, 8 is a disaster now. Is after wake up, I find that it's time for me to disable interrupt. But so unlucky that I find the S is still 0, so I will go to sleep again. Okay? Understand the process? So that's why there is no 2 simultaneous down. It as if no simultaneous down. Okay? Because you will have a disable interrupt together. No, it's not allowed. So it's 1 going down, and whether you can wake up before another guy, also a matter of the scheduler, as well as we don't allow 2 processes invoke the same interrupt together. Okay? And what is the results? The results will be something like this. The results are something like this. I have the first guy executing the critical section, and while we're in the critical section, these 2 guys, because the code is so simple, right? I code down. Because I find that you are inside, the door is locked, I will be suspended, going into special sleep. And these 2 guys, both are in a special sleep state. When this first process unlocked by calling it up, then this 2, the drawing is not that good, right? These 2 guys should have a very small amount of time wake up, the status speaker wake up together. And so happen the scheduler choose this guy first. And this guy has a chance to disable interrupt, change S from here, S value equal to 1, silently change it back to 0, change it back to 0, and this guy, so I have a 0 here, change back to 0, silently find that, when I inside this down call, so happen that I find that S is 0 again, so I want to wait for 1 more guy to finish his job. And this guy changed the S to 1. So happened that when I wake up, I find that no other people try to turn it from 1 to 0 is still 1, I can get a chance to turn it into 0. Okay? So this is the true implementation. I mean, the concept is true, okay? True implementation, of course, the exact implementation is not like that, okay? And this is a semaphore. And with this is the best choice, okay? And it's a current choice in every system. And later, when we come back, we will talk about 3 classic examples. Classic examples, number 1, how to implement a pipe allow multiple consumer and multiple producer. Okay? So there's a general producer consumer problem. Second problem, very classic, okay, even though you never heard of it, it's called dining philosopher problem. Okay, don't spell it wrong. D-I-N-N-I-N-G is another thing. Okay, dining philosopher, you don't look up the dictionary. Okay, dining philosopher problem, what is that? It is the cost row puzzle. Okay, how to control the traffic lights and give the road system the highest throughput. Okay, the last one is database problem. The database problem is we have several readers, we also have several writers. How to guarantee the highest concurrency at the same time, don't allow, let's say, multiple writers to write together, but I allow multiple readers, right? You are calling select and where. You are also calling select and where. Why don't you allow you to run together? Because you didn't change anything on the table. Okay? So this is last problem. We will only cover 3 of the classic problem. If you already buy some of the operating system book, they are more classic problem. What's that? Shopping, sleeping problem, what is that? It's smoking problem. Some of the problem is not as illustrative as these 3. Okay? So I will revisit a bit next Monday over this because it's too important. I have to re-emphasize again about its working. Then we will go into some horrible things. What are the horrible things? The producer-consumer problem is actually not easy to implement. The code is this. You don't need to read the code before because you will not understand. Okay? This is a parallel code, okay? The 2 codes executing together. Let's say how can you control its bound buffer properties together, uphold the mutual exclusion over the data structure. Okay? If you want to look ahead, okay, please do so. Okay, I won't stop you, but we will do the explanation on the coming Monday. So the coming Monday you have several jobs to do. First, hand in your exercise. How many people have hand in?